Hi, so we're going to discuss something called sampling distributions and probabilities. And today specifically, make a little note here, for means. We're going to discuss. You can talk about these things for proportions also. All right, so let's, this is going to be a made-up situation. We're going to consider this example. But we've heard of the ACT. Let's pretend the following is true, that when all the people take the ACT, that the mean score for that group of people is a 16. And the standard deviation of those scores is 5. And let's, for the time being, we're additionally going to assume that the distribution of scores is normal with mean 16 and standard deviation 25. So that's going to be the distribution of x, where x equals the scores of students on the ACT. Okay. So once you have this fact, you can start by asking some simple questions. For example, so let's say you want to know, hey, what's the probability that a randomly selected person, or choose someone of this population of people who took the ACT, scored better than, I don't know, a 25? Okay. So to do that, since it's a normal distribution, we can calculate a z-score no matter what, but we'll be able to calculate a z-score and convert it to an area because we know that the distribution is normal. So this is the same thing as the probability that z is greater than 25 minus 16 over 5, or 25 minus 16 is 9. This is the probability that z is greater than 9/5, or that's, I think, 1.8. Probability that z is greater than 1.8. In terms of our normal distribution, here's what it looks like. Here's our picture. We've got a mean of 16 in the center of our distribution, and we know we're 1.8 standard deviations above the mean, so we're out here. And we get z equals 1.8, and we're interested in that area. Okay. So you can go look up a chart, and usually the chart gives you the area to the left over here. You can do 1 minus that, or we can use the normal CDF function in the TI-84, and that's what we're going to do right now. So we press, here we go, second distributions, normal CDF. And since we have a z-score, we can do it this way, 1.8, comma, huge number. And if it's a z-score, then the mean is 0 of all the z-scores, and the standard deviation of all the z-scores is 1. And we can close parentheses, enter, and we get an answer of about 3.6%. So that's what we're getting here, about 0.036. So it's not very likely to pick someone who got a 25 or higher. That's because my situation's made up. But let's go back and just show another way you could have done this. You could do second distributions, normal CDF. And instead, you could put the lower score, which is 25, comma, the upper bound, some ridiculously high number, comma, the mean of 16, comma, standard deviation 5, and hit enter. And you get the same probability. So that shouldn't really surprise us. Okay. So this is not very likely. Let's try and ask another question. Let's try and find something whose probability is a little bit more likely. So let's try probability that someone got greater than, say, 18. Well, that's going to equal the probability that z is greater than 18 minus 16 over 5. And that's the probability that z, it's going to be 2 over 5, is greater than 0.4. So here we'll get that real quickly. Second distributions, normal CDF, 0.4, comma, huge number, comma, the mean of all the z-scores is 0, and the standard deviation of all the z-scores is 1. Hit enter, and we get about 34%. Okay, so this is a pretty likely event. This is going to happen, at least in a statistics class. We don't start calling things unlikely until we get near around 5%. All right. So let's do something different. Let's pretend now, instead of asking about the probability of choosing a single student whose score is greater than 18, we ask this question. We decide that we're going to take a sample size of n equals 10 students. Actually, let's make it 25. And we're going to find x bar, which is equal to the average SACT score of those 25 randomly selected students. So this is a statistic, X bar, and if you think about it, that's something you might do. You go out and ask, hey, ask 25 people, what did you get in the ACT? Find an average, and then maybe make a conclusion and say, well, that average would be near the average of the population that they came from. So what does this look like? Well, let me give you an example. So take a look at this picture. This is from a website called onlinestatbook.com, and this is a way to simulate sampling distributions. So what you see on the top there is a normal distribution, and this is actually the distribution of scores with mean 16 and standard deviation 5. And what we're going to do is we're going to take samples of size 25 and draw them out one at a time. So if I hit this, you'll see what's happening. It's dropping a bunch of things down. So I'm just going to clear this for a second. Well, wait a minute. And what's happening is that it actually drew out 25 people from that population. So this sample data thing in the middle here those were the results from 25 people. And then this blue one down below is the average, the X bar from that first group of 25. If I hit this button again, here's another group of 25 people being chosen from that normal distribution above. And after 25 little blocks fall down, representing their ACT scores, there's the X bar for those people. So I've done 2 repetitions. I'll do one more. Here you go. So that I picked a group of 25. Here's all those scores dropping down out of the distribution. And then you have the average of those, which will appear down below as a third box. Okay, there it goes again. So what we're really beginning to do here is this blue distribution down below is called a sampling distribution. It is a graph of all the different X bars we're getting as we continually draw samples of size 25 out of the original population. Okay, so now if I press a number like 100,000, what it does is it just does that really quick. And I keep hitting enter and so forth. And you can see my reps over here. If you look on the left of the screen where it says reps, so we're up to 600,004. Okay, I'll fit a normal to this. And what you'll see is that looks kind of like a normal distribution. So this is something we shouldn't be surprised by. What we're saying is this. The distribution of X bar, the possible averages you can get, is also normal. And it has the same mean as the population, which in our case was 16. And that comes from facts we've learned before, but that the standard deviation, or the mean of the population, should equal the mean of all the possible samples that you can pick of a given size. The standard deviation formula is a little trickier. It turns out that the standard deviation over the rad of n is how you get the standard deviation of all these X bars. And if you think about it, in our case, n was 25. You have the standard deviation of x over the rad of 25, right, which is standard deviation of x over 5. That's telling us, if you look at this fact, it's sort of promising us that the standard deviation of X bar is going to be smaller than the standard deviation of the population. And that's confirmed if we look at our graph here. If you look at the original distribution up top there, the black one, that's the parent population, or the distribution. And then this thing in blue down below, this is the sampling distribution. And you'll notice that it's centered around the same place. So they have the same mean, but the standard deviation is definitely smaller. And as a matter of fact, if you look over on the left, it's saying right here that the standard deviation is equal to 1. Well, let's think about that for a minute. The standard deviation of this normal distribution, according to our formula, should be sigma of x bar should equal sigma of x over the rad of n. Now, just so we don't forget, if we go back to how we started this story today, we said that the standard deviation of the population of ACT scores was 5. So if we go back over here, the standard deviation of x bar would be 5 over the square root of 25, because we took groups of size 25. And if we get 5 divided by 5, there's the 1 that we got. Okay? So here we are. We know our standard deviation is 1. All righty. So now I'm going to ask a new probability question. If You remember before we asked this question, what was the probability that x was greater than 18? Does that mean we were picking one student out of the population of all kids who took the ACT, and we're saying, what's the probability their score was greater than 18? And we got 0.34. So now I'm going to ask a new question. It almost looks the same. Putting an arrow here just to let you know they kind of look like each other, but they're not. Here's the probability that x bar now is greater than 18. So now we're saying, what's the probability that a sample of size 25 students has an average ACT score greater than 18? So when you do our math here based on what we just learned, remember, we know that the distribution of x bar is normal, I should say this, approximately normal, with mean 16 and standard deviation 1. That came from what we just talked about. This means that that's because mu of x equals mu of x bar, and this is because sigma of x bar equals sigma of x over the square root of n. So if we use this stuff and we apply it, we get this equal to the probability that z is greater than 18 minus 16 over 1 now, because there's our new standard deviation. Well, that's the probability that z is greater than 2. Okay, that's about, some of you may know that from the 68, 95, 99.7 rule. But if you think about it, we're much further away in terms of the number of standard deviations. Here's 16. We're a full 2 standard deviations away, which means we're out here in the tail, and we've got a very small area. If you think back about the problem we asked earlier, in this picture, for example, we're only 0.4 standard deviations away. You can see that here, as z is 0.4. So when you draw that distribution, here's 16 in the middle. We're actually much closer to it, a much bigger area. So this new area is going to be smaller. Let's actually get it. Here's our calculator. Second distributions, normal CDF, 2 comma, huge number, comma, 0 comma 1. Hit enter, and you get about 0.023, like we said, about 2.3%. All right, so this probability now, 0.023, or 2.3%. You think about that. Let's compare these two for a minute. It's sort of interesting. We said the probability that x was greater than 18 was 0.34. But the probability that x bar, the average score from 25 randomly selected students, is greater than 18, that's only 0.023. So notice how much smaller this probability is than the one above it. And I claim that you shouldn't really be surprised by this, because while it's pretty easy to pick one kid who might have an average, a score higher than 18, it's very hard to pick 25 kids and have the average of those 25 kids have a score higher than 18. And that's sort of what this is saying. Matter of fact, this number is actually telling us that it's very unlikely to observe this. Thanks for watching.